Then let me explain this quickly. I just wrote it. So earlier I mentioned the thinking process for this one. The best way for this one is, this is a composition. And composition, there's some standard techniques to calculate that. One is using this called a bridge function concept. And what is a bridge function? Bridge function is, suppose you have a function fx, and then they ask you to calculate its composition, f of fx, etc. So n time. And this one, normally that will be difficult to calculate, right? And so you could try to find the pattern and then figure out or doing some smart manipulation. But a quicker standard way will be, for lots of those type of problems, will be introducing a bridge function. So we write fx as this way: fx equal g of g inverse hx. And then we will see this composition will just equal to g of g inverse hnx. And then this hx usually will be something that's really easy for you to calculate. Some linear functions, some of this exponent, anything that's trivial for its composition. So if you find that one, then this composition of fx easy to do. And then how do we find this gx, right? And hopefully you already know. Most likely that the bridge function we choose will equal 0 or infinite at fixed point. Of course, there are exceptions, but then those are the norm for, especially for JMO level. And then what is fixed point? If you don't know what a fixed point, and just refer to a Google search, basically if x equal fx, we call that a fixed point. So we want to come up with a function that's equal to 0 or infinite at fixed point. The reason for that one, you will understand better in the future after you learn advanced math. And at this moment, you just say that's could give you lots of coincidence, so that make it easier. And a standard practice problem will be like this one, a rational one. How do you find the composition, right? And lots of you probably also know, probably I spend unproportional amount of time informing you this, like recursion, if a rational one, so they're the same. How do we solve this? And those are the standard one you need to know. And if you don't, just do a Google search or just post a comment in the Google Classroom, and I can post some related, or lots of you could also just explain to others. All right, so this one. So if you know that problem, that's a concept, then the first two problems is trivial. That's just a special case, 1 over x and x squared. And then with those one, calculating, after you know this function composition, and then figure out the original one, that's easy, right? So that will just give you, for the first one, I think will be 2022. And because of time constraint, so we will not go in the detail, right? Those type of things, you know the concept, you should be able to figure it out. And then the second problem, this first, second problem is a square. So I think that one, if I look at it, I think it's this way. 64, so square. And you can verify this one correct. But this is if we know this concept. What about if we don't know? How can you do it? And those type of problem also relatively easy. What you need to do is thinking the 2022, there are nothing really special about 2022. So you try to change this one to something easier, right? So other than it's a positive integer, I mean, we do function composition, that's unnatural. So change to 1, that's too trivial. And then you could check, how about I calculate, if I tell you this one, f composite twice equal x over x plus 1. What's the function, right? So this, you could pretty easily do the reverse and you can calculate, right? Of course, that still takes some time, but at least that's something you could do. And then based on that one, you could conjecture the value should be that the function you're looking for is this. Right? The same goes for the second one, right? So this is a very important concept in JMO, AMO, JMO. It's you start a problem, even at the first, you solve some trivial cases. And in the past, like in JMO, if you can construct a right diagram for geometry problem, you still earn 1 point. Right? So in JMO, if you cannot fully solve the problem, and we try to start with a simpler problem and then see what kind of hint can provide it, and that it help us to solve this. And that's especially true for some of those combo and even number theory problem. Right? So like a number theory, if you see a problem you cannot solve, then first of all, think about what about they are not relative prime, right? Or if they are relative prime, so take out factor or start with the smaller number and see that they provide you any help. Right? Lots of problem, it just, you gradually crack it. Do not expect you'll be able to, right, from the beginning to the end, you just keep manipulating and then you can get the solution right away. This is quite a lot of back and forth process. So just, if you don't know the idea, you just start small and then keep building. So that's what we want to say for those two problems. And next, let's see, look at problem 3. Problem 3, if we look at that one, let's think about it. This need to satisfy 3 criteria, right? Fn equal Fn plus n. And then F1 equal to 2, Fn plus 1 greater than Fn, right? And we know this, figure out all 3, it's not that easy, but let's focus the main drive for this one. Definitely will be the first one, right? And then the first one, if you understand its function composition, that's end-to-end. This problem is end-to-end. Function composition quite similar to sequence. So this one, this just means an plus 1 equal an plus n. And that one look like that's and you know the fn is related to earlier term. So this one, vaguely thinking this might like a recursive relationship. Maybe if you guess Fibonacci, and then you get the right solution. But if you didn't think of that one, then what you can do, just trying to think from the simplest case. Right? And in functional equation or those type of problem, and think about the smallest, the simplest case that's sometimes probably even more beneficial than you use your existing knowledge of some standard technique and solve them. Like lots of you should already know the Cauchy type of a functional equation, and you know some of the standard procedure of solving functional equation, like plug in values or substitute, that type of thing. And if you don't think about simplest cases, you might miss those. And like Justin got that when he's in the 8th grade, right? 8th grade, he got one problem that he thought he know the solution easily. He solved it probably like a few minutes, but then he missed that the 2 trivial cases, then got deduct 2 points, and that caused him to not doing as well as Erickson and didn't make the MOP that year. Right, so let's think about those ones. And simple case, you say constant, is it possible? If it's not constant, how about linear? So we could think if a linear, let's say fx equal ax, does it help? And then if you do that one, you find that this will give you a square n equal an plus n. And then you solve this a equal and then of course, you know, I did not take the other route just to satisfy this requirement. So for this one, then yes, this is definitely not the answer. If it's not the answer, you say we try to make it work a little. So let's say fx equal the floor of this. And if you use this way, it will satisfy the first requirement, satisfy the second requirement, but does not satisfy this f1 equal to 2. So what we can do is thinking, I want to add another constant, but the constant right is small. So we could, let's say, add a constant b. And then you check what's the requirement on b. And when you do this one, what you want to do, plug in the original one, right? Because you plug in b does not necessarily mean it will satisfy the first equation. And satisfy that one, and then you try to find out the requirement on b, and that's with floor functions, lots of the integer part you could take out and then make use of the earlier condition, a squared n equal an plus n, and then you get a requirement on B. And then that one, likely you'll be able to bound those between 0 and 1. And then you will be able to get, I think it's, I'm not sure whether it's a unique one or most likely a few is in the range. But then if I guess, I would say try to check something like has some relationship with the coefficient of x. Most likely is this one. This is a positive number, less than 1, and then you see this relate with kind of Fibonacci type. This one works. And that's detail in those ones down here, because our target is for people who want to be able to do well. So I don't want you to get mingled in those minor detail. And mainly we want to focus on the concept. But then as a beginner, you probably should just have work out all of this on your own to make sure you'll be able to understand everything, and you can get to a point you can discuss to others. So that's why yesterday I mentioned that that program we have, right? So we want to like collaborate and share experience, help yourself, help others, improve. That's what over time, like Sean and Justin did, and then later, like Aspen, Eric, and sometimes Raymond joined it. Even before that, and even though at that time when they were young, we didn't exclusively focus on JMO, AMO, but then when we started with like Sean, Daniel, Justin, etc., we kind of doing the same thing. Even though at that time it's I lead most of the discussion, and like later one, they can do their own. So we want to have that atmosphere among you guys. And if you read anything interesting, and you shouldn't be content that that should be correct. You want to be able to formally write them down, and then we will grade it and comment on those, and then share among our groups. Right. So those are the thinking. So this one, the problem 3 thinking is just unrealistic to think you'll get the exact solution on your first try. So get approximate and see where we lacking, right? So down here, we know if we put a equal square root of 5 plus 1 over 2, this f1 equal 2 does not satisfy. So what we do, we think, can we modify a little bit? And so this type of minor adjustment, very useful in those construction type. And today probably we did not have time to do that one, but in the future, I can give you some of those construction problem, and then those ones, there's no formal way to govern you, right? Like probably some of you heard about the Kirkman problem. And those kind of construction. The Kirkman problem is probably don't want to digest that one, but you can, if you're interested, you can check. And those, even though some of the more famous one, they have a strong serological background, but it's unrealistic to expect you know everything. So just say, if they assign this one as a computation problem, definitely should be solvable using the knowledge you already know. So what you do, just adjust. And if you get to a point that you cannot adjust, okay, that's sometimes that's probably lead us to new solution. Like if you solve a Delphi equation, you could first check out a few smaller value, and then if you find out this one has no solution when the value is small, you probably conjecture this Delphi equation has no solution, right? That's a probability-wise that is correct because it's already proved. The likelihood for Delphi equation to have integer solution is close to 0. So expect that one has no solution. That's likely to be right. And then you try to prove it. If you get to a point, you see that part I cannot, for special type, I cannot prove. Then maybe that indicate for that type, you could have some solutions, and then you just try to see whether you could construct a solution for that particular type, right? So this kind of always think background first. Right, so next we will get to some of the more formally like functional equation. Like problem 4. Ask you to find all such function. So anyone know the solution for that one? And just like we mentioned earlier, this one, you probably don't want to just assign. Lots you might, I'll just assign F0, Y0, see what we get. But then if you do that one, you get F0 equal that's one. And then if you choose 1, etc., still not very good. So do not immediately get bogged down on detail. Try to see the general. This general one is quite symmetric. And do we have one that satisfies this clearly? Fx equal x satisfy this one. And then you could explore a few other. Think about the degree of this. Think that if it's a polynomial, what about the degree, right? So doing the degree also a pretty useful technique. And then if I couldn't find other thing, then your mind is thinking, maybe this is the only one. And if this only one, we try to figure out what's the requirement on this function. So first of all, let's think about when the function, you need to know there's some basic term. Like, what do we mean by function to be injective, surjective, bijective, right? Yeah. Hopefully, if you want to be serious about JMO, those you definitely need to know. Bijection, I think most of you should already know, but probably a little vague on the first two. But if those concepts are clear, you have a little advantage. That's why you know, one of the kids got the JMO honorable mention. And part of the reason I have confidence in him is when I first met him, and he has a very clear idea about this. That's, of course, that time he's already a ninth grader. All right, so 8th or 9th, I forgot. 9th, I think. So this one, let's think about can we show this one is injective? So that means if you have two function values the same, then plug in the original one, you get y1 plus square x will equal f x squared plus fy1 equal f y2, and then this y2. This type of simple manipulation, that's you should feel really comfortable with this. So that tell you this will indicate y1 equal y2. So this one indeed is injective. And next, you let x equal negative x. Right. And just said there's more than one way to solve a problem, and there's so they just demonstrate you one of the ways. If you have other ways, especially if it's significantly better than mine, and welcome you to suggest it. Most of the time, I will try to use the relatively efficient way, but sometimes to demonstrate a point, I probably use the method that's not the fastest. So if you substitute this one, then you will be able to get y equal, no, y. And then this. So that tells you fx will either equal f negative x or f negative x equal negative fx. And then because this is injective, that means when x not equal to 0, f negative x cannot equal fx. So that means f negative x should equal to negative fx. And then f negative x and fx cannot be 0. So that indicate f0 must equal to 0, right? Because the function is from all real to real. So 0 should have its image that must be 0. And then at this point, you can let x equal to 0. And then if we let x equal to 0, what do we get from here? F of fy will equal to y. And then this tells you any real number x, you will be able to get f as y. And some of this thing at the beginning, you might feel a little why we think of this. And this one, if you experience it, and we just kind of revolve around this property of the function, like function bijective, injective, odd, even, its domain and range, and doing this kind of. And so this will take fy. So that tells you this f is increasing. So f increasing. Next, what we want to show this, because our goal is try to show this fx need to equal x. So we try to get some contradiction, right? And y prime equal x squared plus y, definitely greater than y when x not equal to 0. So that means fy prime greater than fy. So here, if exists x, fx greater than x, then from this one and then this one, you'll be able to get f equal fx. This will greater than fx, will greater than x. Right? So that's a contradiction. That meaning fx must equal to x. And then that's just done. So just of course for this particular problem we did a little faster, and then also why we choose that particular property. And for experienced student, that's kind of trivial. For youngsters, you probably want to just redo it and just understand, okay, there are some of those functional equation type of problem I can just solely solve using this property, right? And then you gradually accumulate your vocabulary of solving different type of problem, like functional equation. There are quite a lot of ways. And do not think, okay, any functional equation, I can solve it just by keep plugging in random values. And indeed, lots of problems can be solved that way, but then you have to know like why you want to plug in a particular value, right? Do not always just try 0, 0. Always, I mean, you could try 0, 0. That's easy, so definitely worth trying. But then you have to know the reason to pick that one, and then if the simple number does not work, what shall we do? Sometimes maybe you plug in a number, sometimes might plug in a different variable, substitute as a different variable, sometimes maybe plug in a function. So that's, if you can just experience this, do that on your own or try to teach, then you will understand what type of problem likely can be done by what technique. All right, so Next one, it's asks you to construct integer coefficient polynomial. Satisfy this. Rational to rational is injective. Real to real is not injective. And this is type of problem. The problem solving technique definitely helps. So you think if you just start by saying fx equal an x to n power plus an minus 1 x to n minus 1 power all the way to a1 x plus a sub 0, that's almost impossible for you to check whether it's a injective, it's a bijective, or it's a sorry, I said it should be bijective, not injective. So this F Q to Q is bijective. I mean, for this problem, let's stick to the injective. For the bijective, probably a little harder to do. Injective, we definitely should be able to. Okay, so we think integer and it's construct. So they didn't ask you to find all. So you had the freedom. Then you definitely want to think small. And starting from linear. Linear is bijective for real to real. So, and then if you multiply a coefficient, that wouldn't change the property, separate the rational with irrational, right? So linear definitely cannot do. And then if we do a second degree parabola, and that's not injective. So that indicates this need to be at least third degree. Third degree S cube. S cube clearly is a that is bijective for real to real. And then we need to add some term. Add some term that definitely should be subtract, because if you add, that will two strictly increasing function, and that's still strictly increasing. That's still will be in bijective function. So subtract what? So you want this one. That means in rational domain, this one will have exactly one solution. And then in this real domain, it should have two solutions. So this one definitely should be an integer coefficient. You could put in A, or we just trying to think directly SQ minus X. Down here is 1. You feel if one, that's kind of hard for you to like limit things. So maybe some number. So I think 2 works. 1 does not. Let's check. And if this one does not work, and we see where it breaks, and then see how we can modify this. So for this one, let's see in rational. In rational, if we have two value equal, I mean like x1 cube minus 2x1 equal x2 cube minus 2x2. Solve this one, you get x1 minus x2, x1 squared plus x1, x2, constant term should be x2 squared minus 2. And for this particular one, and we want this to have this one, the equal does not the root. We want this correct one to have two root. To have two root, we can solve one in term of the other. And so like x2, if we regard this one as an equation about x2, x2 will equal negative x1, 8 minus 3 x1 squared. And then this one easy to see, if x1 squared less equal 8 over 3, then we have two solutions. That's not the injective function. So for this real to real is not injective. This one is okay. But then for rational, we want this one to be a perfect square. And down here, perfect square is in rational sense, which means you have 8 minus 3x squared equal y squared. Xy, it's a rational. So I use x2, so 3x1. This one, you let this x1 equal, say, a common denominator n over m. That's y equal L over m. And simplify this one, you get equation. The equation is what? 8m squared minus 3n squared equal L squared. This one, that's a basic number theory. Easy to see. Indeed, this has no solution. You just do a mod 3. Easy to see. And then done. If we choose, let's say down here, if we choose different number and then we don't have a way to show this, then what you want to do is just do not easily drop this approach. Just think about, do we have a different way, right? So where it does not hold, you just multiply it. Right, so this one done, and then let's just do one more problem. And then, so number 6, it's a little bit interesting. That's some of the technique we could use. And then number 7, that's a very standard Cauchy type of approach, solving functional equations, as well as number 8, right? And number 9. Number 9 also really interesting. So I'll leave this one for you to think, and then could be, let's say, from from this 9 to 13. Of course, 12 and 13, they are kind of similar. So you could if you pick one, write the same. And that they are all represent different techniques in this. And for number 9, my hint for you is you could use the standard substitution and that type of thing to figure this out. But then for each particular problem, you have to focus on the main difference from this one versus the other one. And let me see. Maybe I have to do it here. So, and then I'll go quickly talk about number 6. Number 9, I hope what you want to figure out is special thing is first, the domain x greater than -1. And why they choose this, then you see in second part, it's a 2 range. That is fx over x strictly increasing. It's strictly increasing in those 2 range. And how do we make use of that one? That's the key of solving this problem. And then, of course, the functional equation itself, you probably can see that if you switch the x and y, you will get exactly the same thing, kind of symmetric, right? So focus on those 2 and try to figure it out. So if you do that one, you could get this quite a lot quicker. Otherwise, if you just only substitute the original functional equation with different expressions, that could take you quite a lot of time. And so before I let you go, talk about this problem 6. Anyone has suggestion? Yeah. So William, for that one, it's okay. Yeah, if it's so that's why you see I use injectives, bijective interchangeably. Okay, so anyone figured how to show this, right? Do we have this function? Right, and right, first of all, you have to understand you cannot show any polynomial won't fit. Right. Of course, there is a long approach, but that's involving using quite a lot of theories. And I think if you directly using polynomial and then show this one, even you mention some of the theories, whether those theories are allowed in the proof, even though it's true, or they require you to prove it, that's all lead to debate. So it's better for you to use some approach understandable for your peer, right? Probably you heard about the famous Chinese poet. They called the YEA, right? So he's really famous in Japan. Of course, famous in China as well, but he's probably one of the most famous poets in Japan, Chinese poet, because his poem very easy to understand and simple, elegant. After he wrote a poem, he will recite this to old lady. No offense to old ladies, but at that time, ladies are less educated. So old ladies probably If old lady can stand it, everyone can stand it. So he created that one, so make his poem like widely received. So that's to you is you write a solution, you need to review this to make sure some people with a little less background knowledge than you should be able to understand. Do not take anything for granted. So this one, what we do is, that's one reason keep you a little long. Also, I'm late. I was late earlier. So this one is using fixed point. We don't care what is the function, but where's the fixed point? Fixed point f. This f squared means fx, right? So you get x equal 2 and -1. And then if composite twice is fixed point, you composite 4 times should also be fixed point. So this one, it's x squared minus 2 squared minus 2. So the factoring for this one is what the factoring for this one? I think x squared minus x minus 2 squared minus x, not minus, plus x plus 1. Plus 1 minus 1. Minus 1. 2. And then if you ask me why I know the factoring in this one, the key lies the old fixed one should also be the fixed one. So we know one of the factors definitely will be x squared minus x minus 2. Otherwise, I won't be that quick of giving you this factoring. Right. Okay, so with this one, you get 2 more fixed points. So that beside this one, you get the other one, alpha equal -1, so like -5, -1. Those two also fixed point. And then next one is kind of a key. We directly plug in, you'll see you just get them equal. And we see what about we calculate this one. If we calculate this one, this is just equal to, this is f alpha. So that means f alpha also fixed point for this f4. And then that means need to be one of these 4 values. And then cannot equal alpha, otherwise that will be, if it's fixed point for fx, then it should be also fixed point for f squared x. That should be 2 and -1. So this cannot be equal to itself. So if f alpha equal to 2, is it correct? Is it possible? What we do by definition, let's say alpha. and then put this using this property F alpha, and this one should equal to this one will equal F2, and then F2, by the way, it's a fixed point 4. This will equal. So with this one, that indicate it's a fixed point for F2. So it should be 2 or -1. Alpha should be 2 and -1. Contradict alpha. It's not those, right? So we know this cannot equal to 2. And then let's think about if alpha equal to -1, you could do same way and show this cannot be correct. And now we already show you alpha cannot be equal to alpha. So next will be beta, right? And is it possible? If this one equal beta, then you will have F beta equal alpha. Then this one F beta equal alpha. That still shows you it's a fixed point for F2. And that's equal those 2 and -1. So this is contradicts. Now you see it's a always give you contradiction. So that means this kind of a function does not exist. And then this problem done. All right, so sorry to keep you waiting. We'll stop here. And then, like I said, that suggest you try 7, 8, and 9. And of course, if you understand 9, then this 10 also relatively doable, right? That's 10, 11, those standard functional equation problems. To do well in JMO, you need to know how to solve those basic ones. 12 and 13, those ones are same type. And there is another standard technique that can help you solve this. And you could do a Google search. I think you should be able to find a solution. And then you can read it. And then if you like, you can write out a solution. You know, of course, if you join that our discussion group, and then we'll agree them and then share among all of us. All right, so I think that's it. And if you have questions, so that's for the grader, you cannot expect him to know every specific theorem that you know of. It should be the common one, right? So like preferably something you have seen in the official solution sometime before, right? If at least you shouldn't say, they give you a problem, you say this is just a special case for that theorem, and when that value equal to this, like so this one sentence thing, even though it might be correct, most likely it won't get you full credit. And if you cite that one, if you say something, you need to be prepared, write a full proof, all the way linked to the very basic one. And on the other hand, some of the basic knowledge, let's say the Cauchy, and you don't need to do the whole process. But of course, in JMO, AMO, I think the trend, they wouldn't give you a formal Cauchy problem and then ask you to go through the step from integer to, from positive integer to all integer, then rational number, then real number, using this monotonic or this continuous. Those type of approach probably they would do. And for Cauchy, maybe in the end, after some smart transformation, you get those one, and then you could directly cite Cauchy. But then anything more absurd, you should be prepared to write a formal proof. Right? Like in combo, there are quite a lot of different theorem or different results. Some of the common one, like Ramsey number, that you don't need to write. Even maybe like this R33, everyone know, but like a 4-4, those, I don't think they will test you that one, but if indeed needed, I think those one probably you can also cite. Euler, that you can definitely use. But like the one I mentioned at the beginning, Hawkman, not Cookman. That one, one probably they will, I mean, the Cookman is about combinatorial design, right? And if they indeed have those problems, they will expect you to give out the design. And you cannot just say, okay, it's just a Cookman, then it's a when value equal something, and you didn't bother to write down the detailed construction. Then if you do that one, you won't be able to get credit. So Cookman is this one, if I recall this, like 15 boys. And then I'm trying to recall off my head, a 5 group of 3, and then go on a hike. And so that number should be 7. So ask you 7 days, in 7 days, can every pair of boy occurred once in exactly one group? So that means like you want to go out with friends, right? Trying to be special to him. And so you want to be in that group of 3. So is that possible? This is Cookman. And this definitely, for this particular problem, this is a case k equal to 2. But if you only say this Cookman k equal to 2, and then you didn't list all those cases, you won't get much credit. And right, so because some of those problems could be, the general solution could be quite tedious. It's probably impossible for you to give the proof on the spot. Those are professional mathematicians. They spend some time solving those. And they don't expect high school students. They will give you some special case. If you know the best theoretical background, definitely give you an edge. But if you don't know, you could still afford to construct this. Some of this construction, if we have time, we can discuss sometime in the future. What we do is we can do this, put them on a circle and then do a rotate. And with that way, it's mechanical, but you get the required arrangement. All right, so we'll stop here.
Okay, so I guess if you have any questions, you can just send it quickly to the GLE account. And if not, well then I guess thank you for coming and I hope you have a nice weekend.